Welcome to DC Review, Part 4. My name is Jim, and today we're going to be talking about a device called a diode. I'm not going to call it a rectifier because that's a function that a diode could do. So the symbol for a diode is like this. It has an arrow, a line, conventional current flowing through it will produce a plus and minus drop across it, and the value of that drop varies in a logarithmic manner as determined by Shotley and his team back in 1947, and it's actually kind of a difficult equation to solve. It doesn't simply require manipulation to get the variable on one side, because you have to use a method to figure it out. Fortunately, in industrial electronics, we're not too interested in the specifics of this, where in other classes you may be very, very interested in the specifics. We're just going to treat this like a power rectifier. Now, later in the history of this here, the engineers at General Electric came along and introduced another component in the Shotley's equation, which took into account the bulk resistance of the silicon, so this actually ends up being a little bit wide or spread apart further. So, in our purpose here, what we're going to do is use a model that approximately represents this operating at a common voltage, and what that model is going to look like is that when current is flowing, this is important, when current is flowing in this direction, characteristics look like this. Simple enough. So this is when the anode is positive with respect to the cathode. The value of this point is 0.7 volts if it's a silicon diode, about 1.4 volts, didn't mean to put that there, if it's an infrared light emitting diode, like in the remote control of your TV sets, 2.2 volts if it's a red, green, amber, yellow, or orange LED, and about 3.9 volts if it's a blue, violet, or white light emitting diode. So a white LED almost all the time is a blue emitter doped with yellow emitting phosphors that tricks our eye into thinking it's white. So this is a pretty easy model to follow here. It's, you know, just kind of, we can treat this as a battery in a circuit that's series opposing something. Now, the other part of this that I didn't mention yet is that if we reverse the voltage across the diode and make the anode negative with respect to the cathode, what this looks like is an open switch. And the only current that's going to flow through it is the leakage current. So if it's forward biased, meaning the anode is more positive than the cathode by this amount, we're going to say the diode is turned on. And if it's reverse bias, meaning that the cathode is more positive than the anode, the diode is turned off, we're going to treat it as an open switch. So let's take a look at a practical circuit here. We have a 10 volt source, and this is a light emitting diode. We can see that because it has an arrow that tells us it's a LED. And we know from our approximations here that this is about 2.2 volts. And then to find out what the current would be in this is we would take, notice the drop here, plus to minus. Plus to minus. So this is a voltage drop, and to find the current is we need to know the voltage across the 780 ohm resistor. So to do that, straightforward, is that we would just say voltage 780 ohms is going to be equal to 10 volts minus 2.2 volts. And that would give us 7.8 volts. The next step is to divide that by 780, and since I chose these numbers to be friendly, that'll mean that the current flowing through this is 10 milliamperes. So what we have here is a 2.2 volt drop across this, a 7.8 volt drop, DROP, across this, and if we add these together, we see that we meet Kirchhoff's requirement that they add up to 10 volts. So once again, it's always a good safety check. Now we're going to deal with a circuit that's similar, except the diode's in backward. Now the first question you have to ask yourself when you're working with this is the diode forward biased? You've got to know that. In this case, the cathode is going to be more positive than the anode, and it's going to be reverse biased, which means it's eventually off. Meaning that the current flow I is basically 0 amperes. Having said that, I know that the voltage drop, DROP, across the 780 ohm resistor is 0 volts, and the voltage at this point then would be 10 volts. If one side of the 780 is connected to positive 10 volts and there's no voltage drop across this part, then the other side has to be the same potential. So if this is 0 volts by KVL, what we can conclude is that the voltage across the reversed bias diode, that is in off, is 10 volts. Kirchhoff's law is preserved because 0 plus 10 is equal to 10 volts. So you have the additional concern in here of finding out if it's forward biased, and if so, acting upon it, and we won't consider anything in between this. So this is a first level model that we can use to analyze this. Now, I haven't addressed what goes on in this circuit, in this graph, when it's reverse biased, and I'll do that right now. So this is going to be quadrant 1, where we're dealing with a positive voltage and a positive current, and this is going to be quadrant 3. Now, as this voltage is increased, and let me make this as a variable here so we can turn it up and down, is we're going to stress the part, and there's going to be a bit of leakage flow, and then it's going to reach a point where it breaks down. Now what that means is that the potential can actually rip electrons out of orbit and cause current to flow. It'll hit a knee and the current will fall rapidly. So right here is what we have is a significant voltage and a significant current, the product of which is a relatively high power, which can destroy the device. Now some devices are designed to operate in this region, and they're called Zener diodes, and there's some others in their family, precision diodes, and as long as they're designed within the safe area of the power dissipation, they are quite capable of doing a good job of regulation. But a light emitting diode or a conventional diode is not designed to operate in breakdown. So much so that LEDs typically are specified with the reverse voltage rating of 6 volts. Their purpose in life is not to block voltage in the reverse direction. It's to take electrical energy and convert a part of that into light energy, and that's called efficacy. It's like efficiency, but the quantities aren't the same. Now we can end up with all kind of cockamamie circuit arrangements, and here we see some interesting and relatively unfriendly things. We have negative 2 volts and negative 14 volts here, a 1K resistor, and a light emitting diode. And the first question we have to ask ourselves is this guy forward biased? So what I can see is that 2 volts is less negative than 14 volts, meaning that the anode is going to be positive with respect to the cathode. On the number line, if this is 0, here's negative 2, and here is negative 14, we see that negative 2 is closer to being a positive number than is negative 14. Therefore, this would be forward biased, and the way we would find out what the current would be would simply be taking the difference across this. I could call this A, and I could call this B. So I have V, A to B, equals VA minus VB, and that would be equal to negative 2 minus a negative 14 equals 12 volts. Next, if I know the voltage drop across this, and we'll say that this is a green emitter, is 2.2 volts, All I have to do to find out what V1K is to take the 12 volts that we have impressed across the circuit, this is not referencing ground, and subtract from it 2.2 volts, which would give us 9.8 volt drop across the 1K. That's not referencing ground. Now if I have another circuit that's drawn in some strange way, first question I ask myself, is the anode more positive than the cathode? And what I can see from this is that clearly the anode is more negative than the cathode. Hence, this is reverse bias, and this looks like an open switch. So the voltage across the entire circuit here is going to be 7 volts. The voltage across the diode, which is turned off, is going to be 7 volts. And since no current is flowing because the diode is reverse biased, we have a 0 volt drop across the 1K. So KVL is again omitted. So when you're dealing with diodes, silicon or light emitting diodes in DC circuits, you would treat them as you would a fixed drop using our model. So I could say plus and minus 10 volts. A resistor, I might as well treat that lead as a plus minus 2 volt source. It's the same thing. The analysis of this with regard to a light emitting diode is exactly the same. You see that these are series opposing, therefore the total pressure would be 8 volts in the circuit. So that concludes part 4 for the DC review, and thank you for watching.